Hello and welcome to the Daily Space for today, Friday, April 10th, 2020. I'm your host, Dr. Pamela Gay, and I am here to put science in your brain. Do you like relativity? I hope you like relativity because today I've got relativity. And relativity is awesome and weird. And here's what you need to know. Light doesn't have mass, but it has energy. And thanks to good old E equals mc squared, gravity can affect light. Now, since light goes, by definition, the speed of light, gravity can't speed up or slow down light, but it can change its energy, which is visible as a change in color. And gravity can totally change the path of light. This way, the way light bends in gravity is effectively identical to what we do with curved mirrors and lenses of different shapes. And chance alignments between nearby massive objects and distant light sources allows us to see magnified images that aren't just magnified by our telescopes, but are, also magnified by the intervening gravity. The thing is, just like funhouse mirrors and some crazy lenses can warp light in really weird ways, gravity can also twist light to the extreme. And when I say extreme, I mean extreme. It was long ago realized that black holes should have the capacity to bend light effectively into orbit around high-density objects. This is nearly impossible to observe, however, because if the light is orbiting, say, a black hole, it's not exactly going to make it to our telescopes because it's in orbit around around that black hole. Now, there are exceptions, and exceptions are how we sometimes are able to accomplish science. A multi-institutional team led by Caltech's Riley Connors has found a way to see this kind of light. They just needed the help from some dust. The stellar mass black hole XTE J1550-564 is actively feeding on a binary star companion, and the mass it pulls off forms a small accretion disk that emits light. And like all regular matter, is also capable of reflecting light. It's this ability to reflect light that makes the impossible possible. In this system, the superhot disk emits light that is bent by the black hole, and that new path can return light that left one side of the disk back to the other side of the disk. Now, here is where this gets trickstery. These researchers used archival data from the now retired Rossi X-ray Timing Explorer to try and discern which photons were coming directly from the disk and which photons reflected off the disk. This sounds like a crazy feat, not going to lie. But X-ray photons are so few in number that some X-ray researchers will periodically name their photons. There's really not a lot of photons. By looking carefully at the light, they could measure the tiny color differences between directly emitted photons and reflected photons. Future work using this technique has the potential to be even able to measure the effect that rotation has on how black holes warp the space around them. But for now, this new technique is enough to just confirm relativity in yet one new and awesome way. And yeah, they, photon by photon, figured out what was going on in this system. And it's kind of awesome. Now, that research wasn't too painful on the brain. I'm going to warn you that where that research left me comfortably thinking we do understand the universe, the next story left me feeling that I need to go back and start over everything because nothing makes sense anymore. You are warned. There are a few simple rules that we use when we study our far-flung universe. We assume the same physics here applies everywhere. We assume that at large enough a scale, the universe is the same everywhere. That's a simpler way of saying it's homogeneous. That's the fancy word we use. We also assume that what we see happening here at large scales is actually happening everywhere. That's where we get the idea our universe is isotropic. Put together, our universe is homogeneous and isotropic, and the same physics applies everywhere. This is our cosmological principle, and it is at the heart of everything we do when we model our universe at the largest scales. We haven't been able to directly measure these assumptions, though. Well, until maybe now. There are different things in our universe that physics tells us should all give off the same amount of light. Hot gas, for instance, obeys standard gas laws and should glow with consistent luminosity when heated to a characteristic temperature by, well, the crushing gravity of whatever system the gas is in. In theory, if we see systems of similar temperature, we should see them glowing with the exact same luminosity and appearing equally bright when placed at equal distances. In theory. But apparently we don't actually see that. PhD researcher Constantinos Migas unexpectedly made this discovery while looking at 800 galaxy clusters across the entire sky. The distances he used were based on the observed redshifts of the cluster, the observed recessional velocity caused by the expansion of the universe. If the universe has had the same expansion velocity everywhere at any given moment in time, this means that t equals 2 billion years, everywhere in the universe is expanding the same way. If this was true, all objects observed at the same recessional velocity will have the same distance. And standard candles, objects that all give off the same set amount of luminosity, will all appear equally bright. This is like at the heart of everything we do in cosmology. Again, though, this isn't what was seen. What was seen was galaxy clusters at the same temperature and same redshift had different brightnesses. This implies that all else corrected for, these systems aren't actually at the same distance, and the expansion of the universe is not the same everywhere. This throws our cosmological principle out the window. In mapping out these variations, they found smooth changes over the sky, and it appears they can't explain these results as just intervening dust that might be blocking some light or any other naturally occurring phenomena that we know about. This variation isn't small either. This is a variation of 30%. Researchers from multiple institutions did everything they could to figure out what this graduate student had accidentally found while doing an otherwise perfectly reasonable all-sky big data analysis of cluster X-ray brightnesses. They couldn't make this result go away. It appears to be real. And I'm going to try and get this young researcher on the Daily Space to talk about these results because I personally want to know what it feels like to accidentally turn our basic understanding of the universe on its head. I mean, can you imagine going into your advisor's office and saying, I don't know what I did wrong, but it looks like the universe is broke? Because that's what this is. If this universe proves true, everything is about to get a whole lot more difficult to study. And this early career researcher may be in line for a whole lot of awards and a more interesting career than they ever may have expected. But for now, I'm not going to lie. This result kind of hurts my brain. And we're now going to switch gears to a much less universe-breaking result. No relativity was harmed in our next story. In our final story of the day, we'd like to note that a team of researchers has taken lessons learned from studying Jupiter and Saturn and applied those lessons to studying a nearby brown dwarf star. Specifically, planetary scientists had realized that if you use radio telescopes to measure the rotation of the core of a planet from its magnetic field, you'd see a different rotational rate than, well, if you look at the surface. The difference in these two rates had to go somewhere. That energy had to go somewhere. And in this case, the energy was lost to the wind. Literally, it was lost to the planetary wind, to planetary outflows. Thanks to spacecraft at Jupiter and Saturn, it was possible to physically measure these winds and check out what all the relationships were. And it turned out the relationship between the inner rotational rate, the outer rotational rate, and the wind can be expressed in a straightforward set of equations that should be applicable to all similarly structured objects. And here is where one day astronomer Caitlin Ehlers had the realization that brown dwarf stars, well, failed stars, count as similarly structured objects. And she realized no one had published on this application before. Ehlers and her team used data from the Spitzer Space Telescope and the Very Large Array to study the nearby brown dwarf, 2-mass J1047 plus 21, which is only 34 light years away. These two sets of data allowed them to measure the dwarf to be rotating once every 1.758 days on the inside and once every 1.741 days at the atmosphere. And this difference results in a wind at 650 meters per second. This rate matched predictions on how wind speeds should change as objects gain mass, going from Saturn to Jupiter to these 40 Jupiter mass failed stars. This is a cool piece of science, and it shows that we really need more interdisciplinary thinking, with astronomers and planetary scientists, as well as geologists, all taking time now and then to learn from one another. And that's just a cool, easy on the brain story to end on. And that rounds out our show for today. This has been The Daily Space. I am your host, Dr. Pamela Gay, and I wrote today's episode. The Daily Space is produced by Susie Murph and is a product of the Planetary Science Institute, a 501c3 nonprofit dedicated to exploring our solar system and beyond. We are here thanks to you. Your generous contributions, your subs, your bits, and all the volunteer work you do allows us to do what we do and allows me to pay Susie and Annie. Please help me pay Susie and Annie. Thank you. So thank you. Thank you for all you do for us. Okay, I'm going to very briefly answer questions. I do have a telecon starting in 10 minutes, but I'll do what I can. And as I said, I'm going to try and get people from the Universe's Broken Story to come on because I fully acknowledge that I can't answer all your questions, but I'll do what I can. All right, moving the chat closer to where I can read it. So Michael asks, do stars have winds? Yes, like our sun's solar wind that when it has particular bursts of particles in it, we see as the aurora, the solar wind that constantly pushes on the tails of comets. All stars have winds, but the force behind their wind is a function of the energy generation in the core. And in the case of brown dwarfs, Jupiter and Saturn, they don't have energy generation in the core. So it's simply a facet of how they're radiating away their existing heat. And that's why these objects can all be treated the same. So Jillian Georgine says, I was watching Paul Sutter talk about the broke universe, and he was saying there's an extra amount of error in this result or something like this. But you were saying people have already tried to investigate this result. Do you think this will be one of those oops dusts moments? I don't think it's going to be oops dust. am concerned it could turn out to be something else, because if you look at this result, it does have this bilobed difference in different hemispheres kind of look to it. At the same time, though, there's this swirly bit over here and over here. So I don't rule out the idea that it could be something else. This idea is particularly intriguing to me because, and I didn't want this to be part of the story that goes out for all time, but one of the things that has been kicking around as an idea is that we exist inside of a void in the greater universe, that it is the gravitational pull out of the universe that is more dense beyond our visible horizon that is causing us to perceive things as constantly expanding inside of our own void. This would be consistent with that kind of a result, showing that the universe has a different density outside of what's visible to us in different directions. Yeah. Oh, I thought I meant surface winds. So solar wind that we encounter at our distance starts out as a surface wind, and then it continues to be carried away. Jupiter and Saturn with their magnetic fields work in much the same way as a very scaled down, less energetic star. And so we do see the same physics. Henny asks, do accreting black holes have winds? Their accretion disks have winds. The black hole itself just eats things. That's what black holes do. So Veronica Cure asks, how does the size of Jupiter compare to our sun? I want to say it's a factor of 100 something, like a factor of some number times 100. Let me look that up. Solar mass in Jupiter masses. It is, I was wrong. It's one solar mass is equal to 1,047.57 Jupiter masses. So it's roughly a factor of 1,000 difference between the two of them. Let's see what other questions you have. Scrolling up to the top now. Okay, I'm not seeing. And there we go. Michael asks, is the difference in X-ray color due to the rotation of the accretion disk? It's not just from the rotation of the accretion disk. This is the black hole question. So as this light is getting bent, it's getting, if it was a physical object, it would get accelerated. But because it's not a physical object, the energy of the photons gets changed and their color gets changed as they get bent around the black hole. So this is the color change due to interacting within a gravity field. Now, the reason I'm not using the word red or blue is I don't know what the summative difference is, because you get one color shift as the light gets bent, and you get a different color shift as the light tries to climb out of the gravity well, and I don't know which is the dominant color shift. But between those two factors, they don't balance out to zero. So you end up with the radiation coming off of this disk that has been accelerated, but not actually having a change in velocity. It's had a change in the direction of its velocity, which also counts as an acceleration, and the energy of the photons has been changed. After that change in energy, and then after the climb out of the gravity well, it'll have a different color. Let's see what other things. That may be all the questions. I believe that is all the questions. All right, so I have a telecon starting in 4 minutes because I live in a world of telecons this week. Who would have thunk it? This weekend, I'm going to be doing Astronomy Cast office hours on Sunday, possibly from the hammock in my backyard. It depends on the weather. And we will be recording Astronomy Cast later today in an hour and 40 minutes. This Sunday, if she's feeling up to it and we give her space to still be recovering, Annie may do Sunday Science Hour. But like I said, we give her space to still be recovering. But other than that, I will be back on Monday, and I'm working to line up interviews for all next week. So that's all I've got. And I really need to run to my next telecon. Okay. This has been the Daily Space. I am your host, Dr. Pamela Gay, and I wrote today's episode, which will be produced by Susie Murph. The podcast won't be coming out until after Astronomy Cast because telecon. I will see you soon, and wherever you are, you get to see us because you have been here for us. You have been here with your bits, your subs, your patronage, and your volunteer efforts. All of these things mean the world to us. And if you're new and you want to find out how to get involved, well, check us out at CosmoQuest.org. So, this has been a production of the Planetary Science Institute, a 501c3 nonprofit dedicated to exploring our solar system and beyond. We will be back in an hour and 40 minutes with Astronomy Cast getting simulcast right here on Twitch TV. Until then, go forth and be awesome. Have a wonderful morning, evening, or afternoon, wherever in the world you may be, and wash your hands.